we have discussed about the force acting upon the charged particle in the presence of magnetic field, as well as we have discussed about the charge acting, the force, magnetic force acting upon a conductor, current carrying conductor, which is placed in a magnetic field. So equation for force is F is equal to, that is Q into QE sin theta. This equation, and if you put theta is equal to 0, force will be 0. If you put 180 degree, that is 0. That means if the V are parallel or anti-parallel, then the force acting upon the charged particle will be 0. If it is theta is equal to 90 degree, then maximum force will be acted upon that charged particle. So, for example, if the charged particle is thrown into some magnetic fields, yes, before that you should know these concepts. You should know some notations. For example, if I do a notation like this, if I draw like this means that the magnetic field is the direction of magnetic field which is going into this plane. The magnetic field lines are going like this. It is represented as crossed lines. If I represented dotted lines, dots, this indicates that the magnetic field lines which is coming out of this plane. Magnetic field lines means it is a representation of a magnetic field. If you want to represent a magnetic field, then we have to draw some lines. It is a imaginary lines. So those lines are called as a magnetic field lines. If I draw a dot like this here, that indicates that the magnetic field lines are coming out of this plane. The magnetic field lines are coming like this. So this is represented as a dots. Cross represents the fields which is going into this plane. Yes. Okay. Now, why I wrote the equation is, we have to see the trajectory of a charged particle. Trajectory means it is the path traveled by the charged particle when it is moving in the presence of magnetic field. Yes, let's see. Let's just take this crossed fields. Means the magnetic field is going inward. This is the crossed fields. Yes, it's a crossed field. Now let's say magnetic fields are like this. Now there is a charge whose value is a Q, which is entering this field at an angle of 90 degree. It is moving at an angle of 90 degree. Let me say, if this is the direction of magnetic field, an electron is entering like this. This is an electron, it is entering like this. Now, angle between this magnetic field and the direction of this velocity is 90 degree. So, it is entering that field at an angle of 90 degree. Once it entered here, it will enter like this. Once it entered here, what will happen is, there will be a force acting upon that charged particle. Okay? Then the direction of force acting upon that will be given by a rule called, that is called Fleming left hand rule. Already I have given the right hand. So right hand rule is, rule says that direction of force, when direction of force means it will be perpendicular to the direction of magnetic field as well as the direction of velocity. But the Fleming left hand rule holds good for only one particular case, that is when the charged particle is moving perpendicular to the direction of magnetic field. Then only you can apply Fleming left hand. So, according to the Fleming left hand rule, if you stretch the first three fingers of the left hand, then this finger, this finger points to the direction of velocity of the charged particle. If this finger this is the middle finger, and the middle finger points in the direction of charged particle, and the forefinger points in the direction of magnetic field. Then the thumb gives a direction of force acting upon this charged particle. So this is the Fleming left hand rule. Fleming left hand rule. So this is applicable only when theta is equal to 90 degrees. Yes. Now this particle is entered here. So in order to find the force acting upon that charged particle, we have to apply the Fleming left hand rule. So let me collect this. This is on left hand. So this indicates the direction of velocity of charged particle. This indicates the direction of magnetic field. Then the force field. So this is the direction of magnetic field, right? Magnetic field. This is the direction of a charged particle. Then the force acting upon this particle, which is moving along this direction, is like this. It will be acting like this. So if the particle is trying to move along the straight path, that magnetic field won't allow it. It will drag to some other direction, the upward direction. So the charged particle will move like this. Again, at each point, there will be a force acting upon that charged particle, so that it will constitute one circle. Means it will follow the circular path. So if theta is equal to 90 degree, then the path followed by the charged particle is a circular. So that we have to write here. I hope you understood. At each point, so this is the direction of velocity. Here, direction of velocity. By drawing the tangents, you can get the direction of velocity here. This is the tangent I am drawing. Tangent means a line just touching a curved surface. Here, direction of velocity is like this. Here, direction of velocity. So at each point, direction of forces are towards the center. Direction of forces towards the center. Direction of force here also towards the center. Here also it is towards the center. So at each point, the direction of force is towards the center. So it seems like that the force seems like a centripetal force. Centripetal force means a force which is which is pointed towards the center. That is called the centripetal force. In the same manner, the force is acting here. So that we can give the same analogy here. That means this is a force due to magnetic field. That looks like a centripetal force. That is what we can say is force due to magnetic field is equal to the centripetal force. Because this force due to magnetic field is attracting, which is acting towards the center, which is similar to the centripetal force. That force is also, because that force is also which directed towards the center. Therefore, I am just saying, that is what we can write is, what we can understand is, the force due to magnetic field is equal to the centripetal force. So, here, if charged particle in this way, right? If theta is equal to 90 degree, then the trajectory, I already told you trajectory means it is the path traveled by charged particle. Then trajectory of charged particle is circular. If theta is greater than 0, less than 90 degree. If theta is greater than 0, less than 90 degree, then then path traveled by charged particle is what we have to see. See here. For the initial case, angle was 90 degree. In that case, it will follow like this. It will follow the circular path. So if the angle is not 0, neither 0 nor 90, that means it is in between 0 to 90. In that case, what will be the path traveled by that charged particle? Yes, that is we have to see here. Yes, before that I should say one thing here. Here F is equal to equation F is equal to Q in the sin theta. F means you already know it. Here F is not affected this velocity. The velocity will not be affected by this force. However, the force will, whenever the charge is moving in the presence of magnetic field, it will experience as a force. But its velocity is not affected by this force. But still, you can see some change in directions, isn't it? Here the velocity is same throughout this point because that velocity is unaffected by this force. So force has no control over this velocity. That doesn't control that velocity, that doesn't vary that velocity. So at each point velocity will be same. But if you look at the directions of this velocity, it will change continuously. That means there is an acceleration. There is acceleration because we know that acceleration means it is a vector quantity that has magnitude as well as a direction. If you want to say a quantity as a vector, you should have two quantities. Means you should have some direction as well as you should have some magnitude. Here magnitude is not at all changing, but the direction is changing. Then also we can say that as a vector quantity. That can be called as a vector quantity. So here magnitude of velocity is not changing, but the direction of velocity is changing. That is why this particle will have the acceleration. So that is why, in other words, what you can say is this force will accelerate this charged particle. That doesn't change the value of that velocity. This knowledge you should know. Yes, sir. So if the angle is not 90 nor 0, it is not 90 degree nor it is a 0. Then what will be the path traveled by that charged particle? Yes. Again, let us take the same case here. So you should imagine that I have drawn some lines from here. Or in other words, what we can say is there are some threads I tied to these points. So imagine that those threads are the magnetic field lines which is going inward. So if this is a condition, the lines are like this, that means the threads are tied like this. There are a lot of threads here which indicate as a direction of this magnetic field. To this, an electron is there. That electron is not entering like this. If it is entered like this, the angle will be 90 degree. Angle formed here will be 90 degree. Isn't it? This angle will be 90 degree. For example, if the charged particle is entered like this to this magnetic field. So here angle is not equal to 90 degree, or you can say like this. Okay, let me say like this. See, if the particle is entering like this, then the magnetic field here is 90 degree. Charged particle is entering like this. Entering like this, then the angle is not equal to 90 degree here, will not be equal to 90 degree. Then charged particle enter into this field, again that will experience some force. so that it will move like this, and at each point that will experience a force, but that do not follow the circular path. Okay, let me draw it so that you can get a clear picture of this. I'll rub this. This is the direction of magnetic field here. This is the direction. This is not along this axis. It is not along that axis. So here a charge is entering to this magnetic field, direction of magnetic field. A charge is entering here. One charge is entering. Now, this charge is entering an angle in between 0 to 90 degree. So, it will experience magnetic field so that it will move like this. Again, it will experience a magnetic field, it will move like this. Again, it will move like this. So, this charge particle will follow that path. That is called as that shape is called as a helical shape. So we can say that the charge follows a helical path. So if the angle is not 90 nor 0, neither 90 nor 0, then the charge particle will follow helical path. Yes. So this is the path followed by that charge particle. Then the charge particle is a helix. Is a helix. That is a helical path it will follow. So if you take the velocity at one point, if I take a velocity at this point, this is the direction of velocity here. So, let me draw like this so that I can explain easily. Like this. Let me draw it clearly. This is the path traveled by the charge particle. Let me take the direction of velocity at this point. Let us say this is the direction of velocity of this charge particle at this point. These are the components of velocities. Let me say this is the v double dash. This is a v dash. Means it is a y component. This is the x component. Yes. So here v double dash means it is along this direction, velocity along the direction of magnetic field. If the velocity is along the direction of magnetic field, what will happen is there will be no force acting upon that charged particle. Yes. So this is v double dash. So v dash means it is perpendicular, so that it will experience a force. Okay. So that this charged particle will follow this helical path and move along this direction because of these components. Along the v dash, there will be no force acting, that is why it will follow this path. At v dash, that will experience some force. Yes. This is about path traveled by this charged particle when the value of theta changes. Yes. Then there is one term which we have to understand. pitch of a helix. Pitch of a helix. So pitch of a helix means it is a distance travelled by the charged particle during one complete revolution. This is known as pitch of a helix. Pitch of a helix means it is a distance travelled by this charged particle during one complete revolution. When the charged particle completes one rotation, then the distance travelled by it is called as a pitch of a helix. So pitch of a helix means it is a distance travelled by the charged particle during one complete rotation in helical path. So that is known as a pitch of a helix. It's a complete rotation. So the equation for this as P means pitch of helix. P is equal to this is calculated with the help of formula of velocity. We know that velocity is equal to distance by time. Here I have to introduce a P here. So I can write P is equal to V into T. So the distance is along this path, right? It is moving along this path, along that direction it is moving, but it is following a circular path, helical path. Yes. P is equal to, I am writing velocity along this, it is moving like this, P, V double dash into T. P, V double dash into T. So this is the equation for pitch of a helix.